In this lecture, we're going to take a look at heat engines. Excuse me, and in the same breath, we also are talking historically about the Industrial Revolution, the 20th century in particular, and raise some questions about what our future looks like in terms of energy. It is truly unfortunate that we have just spent so much time burning things. But burning things represents access to energy that's at a high density, which is important for a lot of our industrial uses. On a personal level, though, we can definitely have an impact on energy by trying to minimize what our personal energy demands look like. So let's take a look at this heat engine and how this actually has powered our industrial revolution. Burning. Well, when we're burning stuff, we are accessing fuel at a high level, and we're decomposing materials into their sort of constituent reactants, so or products really. So high temperature, that's the burning part, and then what's left over is at a lower temperature than what we started with. So an easy place to start off with is a wood stove. Right, inside the chamber where we're burning the wood, that's the high temperature. The low temperature is the chimney where the smoke comes out. So in the process of going from a high temperature to a lower temperature, we do something with that energy. So we're harvesting energy at a high temperature and we're exhausting energy at a low temperature. And in that process, we can potentially siphon off some energy into useful work. But because we harvest at high temperature and exhaust at low temperature, we're always exhausting something. So by its very nature, heat engines cannot be 100% efficient. So let's think about how that works. Our heat engines are going to run on a repeating cycle, and so that means that the overall change in internal energy is zero. We harvest at a high temperature and siphon off a little to do useful work, but the rest is going to get exhausted at lower temperatures. So our cars are great examples of this. We run on gasoline, high density fuel. We ignite a mixture of gasoline and air, oxygen, and then that hits a high temperature, it explodes, and then we use the expanding gases to push pistons in our cars. And then that spent fuel is exhausted, and that's what represents QL. Here's another way to visualize this with a steam engine. So our boiler is QH. So that's where we're harvesting a high temperature energy. And we harvest it by allowing steam to escape from the boiler. When the intake valve is open, then the steam rushes in and pushes on the piston, making it expand. And that's where we're siphoning off useful work. But in the process of this expansion, we know that the temperature is going to decrease. So when it decreases, then this wheel is going to continue to spin and push back. When it pushes back, if we close the intake valve and open the exhaust valve, then the spent steam, because it's not as hot as it once was, is now going to go into our condenser, which then we can recycle. So it's here where we have QL. So QH comes in, we get some work done, and then QL exhausts it. A slightly more efficient way of doing this would be to have a turbine. And in our turbine, we have curved blades to maximize the amount of momentum that we can get from the incoming steam. And then once again, it gets exhausted. So you can see that because we have a rotary system, that we don't have a need for valves. And then if this turbine is, the shaft of it is connected to a generator, then boom, There we go. The internal combustion engine also, we talked about this briefly. This needs valves. We have cylinders that move up and down, and they're on a crankshaft. And the crankshaft is where we will harvest torque, really, to turn the transmission of our cars. So intake valve open, and then we have fresh fuel coming in while the exhaust valve is closed. And then both valves are closed as the piston comes around and pushes up and gets really close to the spark plug. Both valves are still closed, and a spark ignites the gas, which now pushes, and the O-rings are sealants, so that pushes. And by the way, there's one car company that talks about, has it got a Hemi? Hemi just means a hemispherical piston here. It's supposed to be more efficient. And then as it comes around again, the exhaust valve opens, and then we can exhaust this gas. And then when it continues to go around, then we can intake fresh stuff. So let's count how many rotations we have. So piston's going down, it's coming around, piston goes up. So that's one stroke. And then piston pushes down. And momentum just takes things around. And so if you're thinking about how many strokes this is a downstroke, an upstroke, and then a downstroke, and then upstroke. So this is a 4-stroke engine. Okay, so a heat engine has to have a temperature difference because heat doesn't flow unless there is a temperature difference. So there's always inherently some waste that's going to happen. So the efficiency, at least from the human perspective, is we take a look at what we harvested and then how much useful work we got out of it. So we harvest QH, and then we compare that to the actual work that was able to be done. And the ratio of those two is efficiency. But you can also express efficiency in terms of just heat. So the ratio of QL to QH, how much we waste to how much we harvest, is sort of a measure of inefficiency. And so if we subtract that from 1, then that turns out that's another way to do efficiency. Now, a Carnot cycle comes up pretty quickly. There's myriads of different kinds of cycles, but the Carnot cycle consists of only isotherms and adiabats. So an adiabatic situation, an adiabatic compression is one in which there is no heat transfer. And isothermals means that the temperature doesn't change. So in the Carnot cycle, we have 2 isotherms and 2 adiabats. And here's what it looks like. So going from A to B, the dotted line shows that the temperature is going to stay the same. So that's an isotherm. And isotherms mean the change of internal energy is 0. So any heat added is going to go straight into work being done. And then from B to C, well, that's adiabatic. So that means that Q is going to be equal to 0. Now C to D, the process is going to repeat itself. It's going to cool. And then we have one final adiabat. And again, Q is going to be equal to 0. Okay, so here's a more modern heat engine. I guess not that, almost modern. Vermont's one and only nuclear power plant, which is now out of commission. It went offline about 7 years ago. At the time when it was At full strength, it was generating about 620 megawatts. So I believe the McNeil Woodchip generating plant is operating around 80 megawatts. So that's the one on Riverside Avenue in Burlington. And so, excuse me. This one nuclear power plant, not a particularly large one either, could have the production of 8 woodchip plants. Now, a couple of things to point out. Notice the efficiency is not great. Excuse me. It went offline right at the end of 2014, and now it's in the process of decommissioning. But the decommissioning of nuclear power plants takes a very long time. And in fact, we don't even have a lot of experience in this country with decommissioning nuclear power plants. It's a rather recent situation. There is fuel that needs to go somewhere. And the process of decommissioning means allowing a nuclear reactor to run out of fuel slowly over time. But then the byproducts of that nuclear reaction, that's typically uranium-235, that goes through a spontaneous decay into component parts, component elements or daughter elements that are extremely dangerous because they themselves are radioactive. So where to put it is a big issue. And so most of the spent fuel for this particular reactor is still on site, in storage on site, and storage actually in the reactor itself. You'll notice that the Google Earth picture shows the relationship between Vermont Yankee Nuclear Power Plant and the Connecticut River. So yes, it's right by the river. Why? Because we harvest energy from the reactor, QH, and we have to exhaust energy somewhere. So exhausting it means dumping it into the river. Now, this is just thermal energy being dumped into the river. It's not like toxic waste or anything, but it does warm the river up. So there are certain standards about the allowable increase in the temperature of the river. But decommissioning this power plant doesn't look like it's going to happen or be complete for another 50 years. And of course, you'll also notice that the Vernon Elementary School is right next to it. All right, kids, be safe. So what happens is then we have an ongoing, essentially, chain reaction, kind of like a bomb, but happening, extending over a much longer time by using control rods. And so they regulate how much heat we get off the reactor. And then that heat heats up water, and then we use the steam to turn turbines. So it's the same old story, really. You can see that there are a number of stacks in the photo below that have steam coming up out of them. And so those are places where we are trying to exhaust QL, and river water is definitely a component of that. But the structure of these cooling towers is a little sketchy. So this was in 2007, and this took a nuclear power plant, took Yankee offline for a few weeks while they fixed this. Now, if we're going to have a reversible engine, then we can talk about the ideal efficiency in terms of temperature now. If this is a Carnot heat engine where you have an adiabat and an isotherm, on that isotherm, when you're harvesting That depends on what the temperature is. So we can rewrite the efficiency, but this is only for the Carnot cycle, and that's important to remember. We can also drive these heat pumps in reverse too, these heat engines. So by doing work, we can actually inject energy into a system, and we can extract heat from a cold zone and then push it into a hot zone. Right, so that's what a refrigerator is. There's a compressor, and then the compressor works really hard in squeezing the air down, then lets it go into low pressure. And the refrigerator should be Freon in this case. So we're pumping and we're generating this gas at high pressure. It's released through an expansion valve and cools quickly, kind of like a snow gun. And then the cooling coils inside the refrigerator soak up the heat. And then QL comes around again, and then that's the story of our efficiency. So we exhaust QH, sorry, we harvest QH, we exhaust QL, and then drive it with useful work. The coefficient of performance is, again, sort of like an efficiency thing. But we can also use heat from the ground to heat us in the wintertime, and that is really useful as well. So that covers the big ideas around heat engines, and then I'll post lessons on applying them. And that's going to be it for the material for our chapter on heat.